So welcome to another problem session. So today it's basically a continuation of our last problem where we did the famous problem on a sphere. Um, you had a block rolling off the sphere and kind of sliding off, and you had a frictionless situation. Somebody asked me a question about what happens if there's a friction on the sphere. Well, so that was yesterday's problem. And if you put a friction in the sphere, I did that problem, and it turns out to be complicates the situation considerably. Okay, so I feel like it's not very appropriate for this series, but it's actually a good problem, and you should do it out. I remember as a student, I tried to do that out at that time, and I got to figure out a whole bunch of stuff. But just today, I try to redo it, and I see it can be very interesting for you just to work it out yourself. All the principles are already laid out. So if you had a friction, whenever you have a friction, you really have to work out the integral for the work on the path of the friction. Okay, so if you want to do work, the energy lost by friction, you really need the force along the way. If the force is varying, you got to do force along the way, and you got to integrate. And with that, I'm going to just move on to today's problem. So today's problem is actually another hard problem. It is a problem that I remember when I first encountered this problem. It took a while to figure it out, but I remember figuring it out and being very happy with that. I had actually figured it out. It's but so if you try this and maybe you don't want to look at this video because I'll give you the solution, and you try it on yourself, you are going to have a ball. Okay, just you are going to be very pleased with yourself if you figure it out. But of course, you're gonna have to go through a lot of frustration, and it's pretty strong learning experience. You have all the principles already. All right, you just because the situation is a little complicated in a way. There's too many things happening, and your brain kind of tries to fool you. It takes a little bit longer to address it for the first time when you see it. But once you see it, it just seems like, why the hell I had trouble? Okay, so here is a ring of mass capital M, and there are two little like another ring on the ring. Okay, so you can say beads with holes which can slide on the ring, and their masses are little m's, and they're sitting over there at t equals 0. You're holding it, because of course it's frictionless, so if you don't hold it, it's going to just slide right away. So you're holding it and it's going to let go at t equal to 0. That's not described in problems, okay? But you have to imagine, but you got to hold it and then let go. Otherwise, how are you going to stay there? Forces are not balanced there. Okay, so like gravity stayed down, but the normal is kind of at that angle pointed up. So it's going to slide down, okay, immediately. All right, so this is what is crazy about this problem is when these two things are slide around, and if this condition is satisfied, if you have at least this condition satisfied, what did I do? If this condition is satisfied among the masses, like if these rings are more than, if mass of those beads, each bead is more than 3/2 the mass of the ring, like pretty heavy beads, okay? Maybe like made of lead or something. So if these beads are considerably massive compared to this ring, at some point the ring will actually start to move up. This is crazy, okay? But so that's what gets you. Like, why would it move up? But once you realize it's all about the center of mass, okay? So um, when these guys going down, okay, uh, so like right now the center of mass is somewhere over here, right? If this guy is very massive, center of mass is somewhere here, and then as these beads come down, center of mass coming down, but at some point it will look like it's going up, okay? So this ring will kind of snap up. Like if you look at the tension here will start to initially kind of, right now if you're holding it, that there's some tension, then eventually that tension kind of goes to zero, and then it starts to rise, okay? So it this pulls this ring up, and it's kind of hard to imagine till you set up the equation. So let's see that we're looking at some angle theta, okay, where this can happen. It rises up. This theta, we're supposed to also find just any theta for any m and capital M, but we're supposed to figure out what's the maximum such theta. Of course, maximum will be when this condition is exactly, maybe we should say greater than equal to, because equal to is always allowed, okay, is allowed in this condition. And this condition is required because you're going to get something like 1 minus 3m over 2m. So if this has to be real, then this condition has to be obeyed. So the real can be is equal to 0. So theta max is exactly when 1 equal to 3m over 2m. So when you figure out arbitrary angle that this thing can happen, you can just set this and you're done. All right. So this is the goal, and this is just a byproduct. All right. So we can just first look at, you can pause the video and try to do it yourself. Okay. So first I'm going to look at the motion of these beads alone, and then I'm going to look at the equation of motion for the ring. So let's look at the beads alone, okay? So beads, so let's see, if you look at some arbitrary angle theta, so whether this happens or not, okay, it's just arbitrary angle theta. So this is a V at some time t. So if you look at the forces on the bead, are going to be normal, and that will depend on the theta and this mg, little mg. This is the force on the bead, and there are no forces, there is no friction, so no forces, no friction along this side, okay? No friction. If the friction, there will be force that way. There's no friction. So there is acceleration this way, and there is acceleration this way. So there are two accelerations here, and this is 90 degrees. So gravity has a component that causes tangential acceleration, and this guy and this guy both have this component. Okay. So that's the force picture. The energy picture is the first thing we should look at. So between here to here, we can do this this V and V equal to 0 we can relate that if I know how much potential energy I lost, because there's no friction. So you have a R here, and this is R cosine theta. So if I look at just one of the beads, so one bead, energy picture is half mv square minus 0. So this is delta kinetic energy, must be equal to delta potential energy. So this was the final, and this is the initial. This is the final, and this is initial. So if you take this as your kind of 0, then that's the change. This is the change will be mgr. It was mgr, the whole thing, and it was mgr cosine theta minus mgr cosine theta. So this is potential energy. Okay, so let's call this equation number 1. And so this is the energy picture. Remember, I've talked about energy first, and then momentum, and then angular momentum, angular momentum, and then the F equals ma. So now we don't know this thing, but we know it's a circular motion, and if we set up F equals ma, we can get that in terms of theta. So in circular motion, we are going to have n theta, which is going out. So minus, this side I'm going to call it plus. So n theta plus mg, this is theta, then this is theta. So that mg is this way, its component will be mg cosine theta. Do you understand this? Because I'm not gonna keep doing this from the, like maybe several videos back, how we get these components. So if this is mg and this is theta, then its component is going to be mg cosine theta. That's what I did. Okay, and this is going to be plus, because if this is the plus direction, and I choose this plus direction because I know in this the direction is v square over r. The acceleration is in that direction, so it's going to be m v square over r. So we can we really don't know n of theta, unlike the last problem where we said it's going to fly off, the n of theta will be 0 there, but here we don't know. It's still in the is moving in contact with the ring. N of theta is not 0. N of theta is not 0, so just don't turn it off like that, okay? But at least we can write everything in terms of theta. That's what we need to know, because using this guy we can get rid of this guy. So let's just process that. So if you process that, 2 on the other side, r on this side, so I'm going to get mv square over r, will turn out to be mg minus 2mg minus 2mg cosine theta. So this is this right side will become 2mg minus 2mg cosine theta. So if you do everything with a minus sign, so the n theta minus mg cosine theta, then this becomes minus and this becomes a plus. So n theta, it just becomes 3mg cosine theta minus 2mg. So Okay, that's how far we're gonna go, because if I go with the tangential one, what we're gonna get? We're gonna get how fast dv is changing. So the tangential will be acceleration tangential will be dv dt, and it's going to create another unknown with a time variable, etc. And then it's not going to help us in this problem. You can just set it up if you want. Okay, it's not going to be helpful. So basically we can write down this 2 prime. So this is 2 is the same as 2 prime because it came from these two guys, right? So we didn't get a new information yet, and we need another new information to get this, and that will be with a ring. Okay, so let's do what's going to happen to the ring. So ring, I'm going to have force picture because we are going to have to use this guy somehow from the ring. So if you look at this force here, this is from the ring on the bead, right? So n theta, this n theta is from the ring. So let's write that down. This is from the ring on the bead. So it's pointed outward like that from the center of the ring. This is the center of the ring. Let's call this center of the ring. This n theta. Now, third law will say bead will push on the ring with the same amount of force but in the opposite direction. So if the bead was here and that's the theta, it will push with n theta. So this is one force on the ring. Another force on the ring will be by the other bead, but because the symmetry is going to be same value as n theta, and of course it's going to be tension T, and tension T is going to vary with theta, so I'm going to write down theta, and there will be mg at this is the center of mass of the ring, so big mg. So these are 4 forces that you expect to be on the ring. If you had a friction, right? If you had a friction, then there will be friction force also. There will be 6 forces. One friction will be this way, because if the friction was that way, then the friction will be that way, and another friction will be that way. So if there was a friction, we would have like that, but we have those guys 0, so we don't write it here. Okay, so far cool. All right, let's do it now. When it goes up, this will be at that time. So okay, so let's write a efficacy statement in general and see, and then put condition on it. Okay, not from the get-go. So if I write this as x and y, then these guys are only guys which have x component and they cancel each other. So there is no x acceleration. So there's only possibility the y acceleration. So m a y for the ring. So this is for the ring equation of motion for the y. So this is the y equation. That should be equal to the t of theta minus mg and 2 of these guys. So this, if you took n theta down here, bring down, so you bring this guy right over at the origin of the coordinate system. If this is theta, then this is theta. So this is n theta, 2 of them, 2n theta cosine theta. So that's all we got. Okay. All right. So that's the equation, and it seemed like this should have enough information to solve the problem. So we need to apply some physical intuition and requirement on it. So let's see what's going to happen. It's saying the critical moment will go up. I mean, the instant, if this goes up at t, okay, then if you look at the t plus dt, there will be y double dot will be non-zero. T minus dt, y double dot will be 0. So at t, we're going to just set y double dot, or this the ay. Ay will be 0, right? This ay. So we are going to set this equal to 0. Another thing that will happen going up, meaning the t will actually at that critical moment will be 0. Okay, and then I've got mg and 2 and theta cosine theta. So I need this equation holds the key when it will go up. Okay. All right, let's just maybe this we just put it here and see what comes up. So let's bring everything on, make everything positive. So I have a 2 n theta cosine theta plus mg equal to 0, and then I'm going to put this 2 3 mg cosine theta minus 2 mg. I tend to make mistake when I just copying on this screen. When you're doing on the board, that's like, wow, that's no problem. There's a huge amount of space, and then you have a better view. Plus mg equal to 0, and let's do one thing. Get rid of this 2, make it 2 down here, and because we want theta, let's call this x. So this is x. And let's do another thing, get rid of the g because the g is the same in everybody. And let's get rid of m and divide by m. Okay, so I've got 3x squared minus 2x plus m over 2m equal to 0. All right, so x equal to 2 times 3. I'm going to probably make 2 times 3 is 6. This is 2 plus minus square root of 4 minus 4 times 3 m over 2 m. Okay, let's take 4 common, so it becomes 4. This becomes 1, and this becomes 1, and outside becomes 2. And let's cancel this 2 with this 2. So you have a 1 over 3, 1 plus or minus is square root of 1 minus 3m over 2m. So this is cosine theta. So these are given, if this is positive, then you're going to get this will be real. If this is positive, this will be real. So this condition is required, this to be positive. Otherwise, this problem doesn't make sense. Okay, if you don't do that, then there is no condition where this will happen. Is completely connected with this condition being correct. Okay. So this is my answer. You can do arc cosine and things like that. So you get 2 angles here, but let's see what will be theta max. theta max will be when 1 equals to 3m over 2m. When this is the case, that's 0. That means cosine theta max equals 1, 3. So theta max is going to be r cosine 1 over 3. So, and this is for any value of this as long as this condition is met. For instance, what if, so an example will be, okay, 3m over 2m is supposed to be less than 1, right? It's supposed to be less than 1. So let's see, this is equals to half. Then you have a cosine theta for this case will be 1 over 3, 1 plus minus square root of 1 minus half. And this is completely fine. 1, 3. So you are going to get two angles, 1 plus minus 1 over square root of 2. And you just have to work out the answer for those two angles. So you are pretty equipped with this relatively difficult problem where there is a critical angle or critical angles at which the ring will start to rise. Okay, I think that's probably it is. I am just going to say that if you have subscribed to this channel, great, thank you very much. If you haven't subscribed, please, it kind of helps to spread the word. So that's one request I have. Another thing is, even if you subscribe, maybe you can tell your friends and other students, other teachers that you found this channel, that this is useful, and there's some discussion of a little bit more challenging problems, prepares you better for the tests. I always feel like if you prepare just barely for the test, when you get to the test, you are going to get stumped. But you always should prepare with the hardest problems, even if you can't do them initially. As long as you're exposed to those problems, exposed to thinking at a little bit higher level, you when you get to the problem or get to the test, you're not going to be as nervous, and the situations that they present will not be as unfamiliar. A lot of the time, when you're taking a contest or test, the unfamiliar situations tend to stump you because you're facing a time pressure as well as unfamiliarity pressure. So it's good to try out harder problems in your textbooks. I'm picking variety of hard problems, easy problems, more like what happens appears in the test, and sometimes some less likely it, but not outside the scope. Okay, with that, I'll see you in another video. Bye.